Prabhu Ramamoorthy from Nvidia. I'm a part of the financial services team at Nvidia. And I also wanted to highlight that I'm also a practitioner. Before this, I was at KPMG running the valuation desk. And I used to do a lot of coding on the banking and capital markets, on market risk, credit counterparty risks on GPUs. So that's how I came into Nvidia. And I've been at Nvidia for the last 6 years. And I can name that we have one partner. Right? I mean, we are very good selective, and that's in one single hand. And KX is one select highlighted partners. And we work closely with them. And we are looking forward to launching new solutions for our customers. I quickly wanted to cover, right, I mean, what have we got here, right? I mean, all our clients are interested in trade ideation, research and execution. So you have a product, right, that is built on that. There's been a lot of news. You probably saw Cloud for financial services, OpenAI doing something with it. But this work has been happening for the last 2 years. We actually worked on this concept of unstructured data integration and structured data integration. And everybody in the crowd knows KX, and we Nvidia are supporting them full-heartedly. And this is a solution that you would be able to leverage the best of both KX and Nvidia. And it would cover all the spectrums: trade ideation, research, execution, for all the functions: front office, middle office, and back office. And we plan to combine data. Right? KX sits on a lot of data, and they can process both structured and unstructured data. And with the Nvidia analytics, it's a winning combination. Right? So we are planning to take this to the various units. And essentially, Nvidia, right, I mean, you'll see some of the work being done, like the integrations done, like they're almost complete. I would encourage all of you to sign up, and if you need any resources from Nvidia, if you need any support, we are at the back. Right? We will make sure that we support all your efforts. And this is actually a blueprint that Nvidia and KX came up together. You can see that we cover both structured and unstructured data. And it's a unified agentic AI, right? Like it has got agents for the structured part. And Nataraj is going to show like the various accelerated calculations, key for backtesting, benchmarking, and value at risk calculations using As-of joins and sorts. And on top of that, right, what we see clients, right, I mean, is the clients are asking for intellectual property. And obviously they create their own intellectual property. And this, I'm a believer in firm-specific models. Right, I mean, you obviously cannot understand financial terms, you have to understand accretive earnings and all that. So this is a solution where you can customize not only the structured data part, you can customize the unstructured data part. You can have a fine-tuned financial model which will help you in your tasks, and that becomes your intellectual property, right? And it has got the highest speed, fine-tuned accuracy. It's your IP, and we are an enabler. And this can also be run with GPUs at the highest latency, best throughput. And we are in this journey together where we can ensure that you can get your end use cases. And a lot of effort has been put into this, and we'll cover those in the demos as well.
Yeah, I think, is this working? All right. Yeah. Yeah. One of the things with Prabhu is that he sets the tempo so high, and then it's left up to me to sort these things out. So firstly, well, this is the WWT labs, where we wanted to set up this sort of on-premises architecture with the best-in-class. So we have the GenAI building microservices, foundational models like Llama 3, VectorDB, Portworx for Kubernetes, Nvidia, Supermicro, Pure Storage, Arista. So essentially, we wanted to see, like, if you have an on-premises setup, what's the best we can do? And we built this product called KX AI Research Assistant. So the idea here is that you have all these SEC filings, can you ask questions and just get answers directly? Behind this, we have an on-premises setup of KDB.AI where we have loaded all the SEC filings, and we're going to just ask questions and have the MCP server, or in this case the agentic AI, respond back. So we have seen, like Connell showed the MCP server, but now the question is, how can we productionize it? How can we take it to market, right? So if I were to just play this. So the first question that we're going to put in the system is, there you go. All right, so what drove revenue change as of the fiscal year 2022 for AMD? What we're seeing here is that in the back end, we have some agentic tools that starts parsing the specific query. So given a query like that, first it extracts the symbols, so we are querying for AMD. It extracts the timestamp, the time range, what is the time range that we're running the query for, what are the relevant keywords, what are the filing types, and then fetching and processing relevant documents. So this is basically showing, we had a version of this where all this was happening behind the scenes. But we wanted to kind of expose that, what's really going on in the back end, right? So in the back end, you have all these tools and the MCP server parsing through the query, understanding the different contexts, and then retrieving the data from KDB.AI. So that's sort of the RAG part. So it retrieves the relevant chunks of text, or retrieves the relevant SEC filings, and then it shares it with the LLM, which is Llama 3 in this case, to produce the output. So the first part is the RAG architecture. At this point, we have retrieved the data sets, and it's being sent to the LLM, and it's processing the results. And it produces the insights. So there's a lot of text in here, which refers to essentially what the question was that was asked. But then we can go a step beyond that, and we can build an entire sort of a quant work test or an analyst work test, where you can ask further questions or do more research, essentially. You can also ask follow-up questions. So what happens when you ask follow-up questions is that we retain the history in memory, and we send the entire context to the LLM, along with the previously retrieved documents using RAG, and the newly retrieved documents, which are also being retrieved using RAG. Now, one thing I should add here is that this is going against 10 million SEC filings, like years and years of SEC filings. It's just because KDB.AI is just so high, it just works so well. It can do this thing so fast. This is all happening in real time, and it produces the results in real time. So yeah, I'm just going to go forward into the video, and you can do a lot more, right? So we have other features: company overview, news, analyst ratings. You can do MEC, you can do overlays of technicals, MECD, VWAP, SMA, and so on and so forth. So essentially what we have here is, we spoke about the MCP server, we have spoken about agentic AI, we have spoken about all the different AI stuff that's going on. This is sort of a realization, a productionization of all these components into a product that's going to be actually useful. Okay. Now there are other agents along the same lines that we are looking into. For instance, the AI strategy miner. The idea here is that you have different investment strategies. Can we cycle through those almost like overnight, right? So you have mean reversion, long short, whatever your strategy might be. Can I use that knowledge, enrich it with the news that comes in for the day, and surface some ideas to the sales trader in the morning? Second is AI trading agents. The idea here is that you can have different trading agents which have been fine-tuned. For instance, you have a fundamentals agent, you can have a technicals agent, you have a bullish, bearish. So you have this orchestration among the agents where they're having a communication. So let's say there's a market shock, tariffs in Japan. Can you have this conversation, almost a simulated trading floor, where you have this multi-directional communication which kind of tries to infer what could be the right trading strategy or the right approach at this point. Now that might not be accurate, but at least you have some ideas that you can build upon. The third one is TCA Explainer. Essentially, what this does is that these are AI agents that combine the data sources for plain language TCA explanation, market impact, performance, POV, dynamic tilt factors, what really happened. Can I use the information that you have in all your algo rule books and kind of provide an answer back. And finally, policy and compliance. So this is with regards to, you have lots of policy documents, and this is an area where GenAI really shines, right? Because it's really good for content generation, content reasoning. So at a high level, what we're trying to show here, what we're essentially portraying here is that, at different stages of the trade lifecycle, pre-trade, trade, post-trade, risk and compliance, you have different ways you can actually leverage your market data, which is in KDB, and by virtue of the MCP server or MCP server tooling, you can get a lot of value beyond just running queries using QSQL. So that was about the MCP server. Now the stuff that Prabhu spoke about, right? The KDB plus transformation with GPUs. So market data to trading signals faster than ever before. We've been using KDB for decades, some of us here, right? So it's the best-in-class tick database in the industry, high-performance interfaces. There have been new innovations. We can saturate all the CPUs. We can maximize essentially the computing architecture. But is there a way we can take it to the next level? Yes, there's KDB-X coming out, but what if I could take the KDB plus code that I have and using some pretty simple operations, make it run even faster? I've been doing KDB-KX, KDB plus Q for many years. You often end up going into the analytics, reviewing the code over and over. Is there a way to optimize this part or that part? But what I've seen, recently in KX is something that I haven't seen ever before. So this is the KDB plus native GPU library. So it's Q native library that offloads KDB plus operators to Nvidia GPUs. What we have observed is 5 to 100x speedups on matrix operations, AJs, vectorized operations. The core idea is keep tables, tensors resident on device and move the compute to data. But more importantly, I guess one of the challenges with GPU has been it's really difficult to set up, and then there are issues. So one of the questions there was, can we make it embarrassingly simple to use the GPU reliably? And to that end, what the team came up with, the core dev team within KX came up with, was something called a GPU library. And what that does, I'm going to show a very quick demo about it, but just before I get to it, some key technical features. Seamless KDB plus Q integration. It's a drop-in replacement for Q primitives. So sum, MEVG, AVG, SDEV. So all these Q primitives, just by using a GPU DSL like G bracket or .gpu, you can have them, you can move it to the device using a .gpu to device function, and then it runs in GPU. So a simple migration .gpu to device and .gpu from device to pull the results back. Multi-GPU scaling with Peach. This is the part that really excited me the most, because we use Peach a lot. And what this means is if you now have 10 GPUs, you can use Peach like we use Peach in CPUs in order to saturate all the GPUs on the board. GPU power table operations. .gpu.select. So we have select. Now currently it supports functional select. So you have the same select statement, except you prefix it with .gpu.select and it runs in GPU. .gpu.aj, .gpu.xasc for sorting, and then .gpu.vwap. And finally, there's several others, but GPU direct for direct disk to GPU transfers, right? So can we bypass the PCI bus latency and go directly to the GPU and do all the operations within the GPU? What we have observed so far is performance orders of magnitude faster, 15x faster end of day sort, faster select performance, 20x faster VWAP calculation, complex TCA, 400x faster linear algebra, and so on. So I do have a live demo, so I'm just going to go through it. Everybody here has been asking me, how are you? I've told them I'll tell you after 7 p.m. because this thing is non-trivial. You know, there's a lot of people working behind the scenes, but to make KDB, which is already so performant, go from 1x to 10x to 100x with such simplicity is a very non-trivial process. Yeah, I think it's coming up. Mm. All right, so this is a notebook that's going to hopefully run. All right, it's running. So we have a number of the GPU primitives. We have loaded the GPU library in here, and I'm going to go through it in detail. So, and I just have a helper function that plots the differences. I'm going to use 16 slaves, and the entire functionality is in a file called gpu.q. So I have a test data set, which is NASDAQ 100, which essentially has all this data in here. So you have timestamp, open, high, low, close, adjusted close volume, etc. In terms of the GPU configuration, this running on a live GPU is Nvidia SMI. So the one that we're using is it's not a very high-end card. You know, this is something you could buy and just connect it to your desktop, right? A100 SXM for 80 gigs. So firstly, I'm going to load in the data. So NASDAQ 100 in Q, timestamp close sim. And let's see what that data looks like. I'm just going to simulate, right? So I'm just going to take about 10 million records, right? So random 10 million records, and I'm just jittering the price just to create some sense of randomness here. So use cases at a glance. There's 6 different use cases that I want to go through. So firstly, end of day sorting. There's a primitive called .gpu.X As-of, sorts large end of day tables on GPU, shortens the batch windows. .gpu.select. So you can run your QSQL, most of your QSQL functions within the GPU, interactive queries, everything. Basically, the code that you have, use it as a drop-in replacement. VWAP on GPU, you can use GPU.select. There's also a more optimized version called .gpu.vwap. As-of joins for TCA, .gpu.aj, custom kernels, matrix multiplication, and so on, right? So let's get to the end of day sorting. I have 10 million records here, and what I want to do is I want to compare on disk, in memory, and in GPU sorting. And all I'm concerned with is, can I simply use .gpu.X As-of to do that sorting? So I save the table to disk, CPU run. So it's sorting, first it's sorting the table on disk, now it's sorting the disk in memory, the table in memory. As you can see, sim time, X As-of, CPU, T directory. So 1.9 seconds on disk, 1.4 seconds in memory. Now I'm going to run the GPU version. So what this does here is it moves the table from memory into GPU, and .gpu.X As-of, it runs the sort over there. So if we compare the timings, this was 129 milliseconds and this was 1.4 seconds. So we immediately have a 14x, 15x speed up just by virtue of switching X As-of to .gpu.X As-of. The business implications are quite obvious. You observe speed up, you have shrinks end of day window, overnight runs, and so on and so forth. But going even beyond that, can we speed up GPU select, which is sort of the base use that every one of us have always are familiar with. So the query I'm going to ask, like volume by sim and algo from 10 million records. These are all the features that are currently supported. Like I said, you can also do Peach, a multi-GPU, the integer floating point. All of these are already supported. Again, just to add, this is a product in active development, but what I'm showing is essentially the art of the possible. So I'm doing the query, the select query in CPU 1521, so 1.5 seconds. And then I run the same query. Now mind you, currently .gp.select uses functional form, so I have it in the functional form in here, and that runs in 145 milliseconds. So we have a 10x speed up. So I basically done minimal change, right? So I've essentially switched from just doing select from to .gp.select, select from, and that the same thing in the functional form. So the observed speed up on 10 million rows, 10 to 14x. I'm almost done. GPU VWAP. Perform VWAP on 10 million records, VWAP per symbol on the GPU using the expression, the VWAP expression. CPU, 89 milliseconds, and it's not a very large table, but nevertheless, like I said, we have to switch to the functional form, and then if we do the same operation in GPU, so we have a 6.36x speed up. Now, if the data is already cached, what you're going to observe is that it just starts getting faster and faster, so now your VWAP is like 27 times faster and so on, or 30 times faster. Transaction cost analysis. So 20 million trade table, 200 million code table, accelerate TCA analysis. What I'm doing here, again, we have to move some of these attributes into the GPU. So I moved the sim, the time, these attributes from the table into the GPU. And well, the interesting part here is that, so binary search is like 50 times faster. So this is what's happening inside .aj, right? So binary search is 50 times faster. There's ways to optimize it even more, but just by using that specific optimization of bin, I have a 3 to 4x, 3 to 5x speed up on VWAPs. As of joins. One other thing, which is okay. It's a complex market impact calculation in GPU. So this is where you can actually plug in CUDA code because we support custom kernels. So essentially using .gpu.jit, you can register the kernel and you can have whatever variation that you want. This is like a simple addition. There's an entire syntax to it. There's a whole description to how it works. I won't go through it in detail, but essentially it's very rich, very robust, where you can do, like, this is a simple example, can I add these numbers to a certain number, and it does it. And then in this particular case, we're actually running a real world TCA calculation where I'm doing it in the CPU, and then I'm going to also do it in the GPU. What it's doing is it's performing 50 as-of joins with time shifts, 0, 10, 20 to up to 490 milliseconds backwards, and creates columns T0 to T49 with mid prices. And it does that in the CPU, and then it's going to do that in the GPU as well. So on the CPU side, it took 17 seconds. On the GPU side, 7 seconds. So 2.5x speed up approximately. And the last example that I have here is matrix multiplication. So, just for the heck of it, I use like an example where I have like 1 million OpenAI embeddings, and let's say I have a new embedding that comes in. I want to do a similarity search. This is basically the flat search in RAG, right? And what happens if I do that same operation? I can do that in matmul, MMU. It's okay, it works, but GPUs should be technically much better. So instead of doing the MMU in Q, can I do the same MMU in the GPU instead? So it runs the matmul first in the CPU, then it runs the matmul in GPU, 230x speed up. And this is quite obvious. You are expecting a speed up, but I've gone from 5 seconds to like 23 milliseconds to find the most similar vector, basically do a RAG search on 1 million OpenAI embeddings, and this can be improved even faster. We have done some benchmarks where this 1 million, we have gone further down to like 6 microseconds. So there's a lot of potential here. And lastly, the thing that I want to mention is that we all know that GPUs are expensive. But this particular example, all of these run on an A100 that costs $1 per hour, roughly $1.8 per hour. So just with a single A100 with 80 gigs, you can get a tremendous speed up, that I frankly, I have never seen before myself. So just to wrap it up, so what does this mean, right? So in terms of the business impact, the technical value is quite obvious. There's a huge value proposition here in terms of the time to execution. Algo trading, 4x more, you could do NX more strategy within the same research window, backtest on the complete tick data, run intraday strategy optimization, market signals in sub-seconds. Market impact across hundreds of time lags, right? Full order book depth, not just top of book. Same day TCA reports, risk and compliance, and so on. So net, right? What we're seeing is that by using the KX GPU library, you're basically reusing the same code that you have. You're offloading your compute expensive tasks to the GPU, and you can reduce time to market, capture opportunities much faster, execution quality, whatever, basis point slippage reduction, quant productivity, enhanced efficiency, and reduced TCO. This is still a product in active development. There's a whole team that's working on this, but insofar, as the performance is concerned, given the amount of time we spend in optimizing Q code, when you have something like this, it almost feels like magic. Like you run this, you do a GPU DSL, and it just speeds up all your code like 10x, 20x, 100x faster. That's all I wanted to show, and thankfully it ran.